Okay, so now let's practice a new form of limit that we've never seen before. How would you evaluate this limit? Because the thing is, the previous limits we've seen they've followed the form f of x divided by g of x, where fx and g of x are just polynomials and maybe radicals. That's it. But we've never seen like complicated fractions, complex fractions, any where fx and or g of x are just rational functions themselves. Okay, like this is pretty complicated. Okay, so in order to evaluate such a limit, we would have to rewrite this into something that we already know how to work with. Okay, so let's do just that. So how would we rewrite this numerator so that it becomes a lot more simpler and easier to deal with? All right, we want to combine the numerator. Okay, to combine the numerator, what you would do is you would just write the limit as x approaches 0 of, you're gonna combine the fractions. So you're gonna get 3 divided by 3x plus 3 minus x plus 3 divided by 3x plus 3 divided by x. Okay, this is what happens when you do cross multiplication. You're gonna multiply the top and bottom with 3, and you're gonna multiply this top and bottom with x plus 3. Okay, and now you can combine this fraction. I'm gonna erase everything. You can combine the fraction and get the limit as x approaches 0 of 3 minus x minus 3 divided by x plus 3, 3x plus 3 divided by x. Okay, this is the same as the initial function as we got, limit as x approaches 0 of 1 over x plus 3 minus 1 over 3 divided by x. Okay, these two are the same. We just rewrote this function. Okay, now what we're gonna do is we're gonna bring the denominator to the bottom and we're gonna cancel these 3's. Okay, when we bring the denominator to the bottom, we get something that's a lot easier to work with, a lot more manageable. So we get limit as approaches 0 of negative x divided by 3x times x plus 3. Okay, now you solve the limit from here on. All right, you think you got the answer? Well, all you gotta do is just cross out the x's. So you now get the limit as x approaches 0 of negative 1 divided by 3 times x plus 3. Okay, so now we've essentially just removed the whole at x equals 0, and now now the function actually exists at x equals 0. Okay, otherwise this function would behave exactly the same, but now this function doesn't have a whole at x equals 0. Okay, so we can just directly substitute 0 for x, and now we will get negative 1/9. So that's how you would solve a complicated limit like that with a complex fraction. You rewrite this into something that's a lot more manageable to work with. All right, now we should explore another type of limit that I'm sure that you haven't seen up until now, or maybe you have, but you might be struggling with. Limit as x approaches infinity of x squared divided by x plus 1 minus x. Okay, I'll take the limit of all of this. Okay, now what do you notice about this limit? It's not your standard f of x divided by g of x, right? Here, you have one function, which is a rational function, x squared divided by x plus 1 minus x, right? If you directly substitute, you're going to get, right, the limit as x squared divided by x plus 1 approaches infinity is just infinity, minus the limit as x approaches infinity is just infinity. So you get an infinity minus infinity case, right? You might think it's 0, but actually infinity minus infinity is also another indeterminate case. Okay, so we're going to do the same thing we did before. We're going to combine this into one fraction that we know how to solve. Okay, so let's do exactly that. So that equals the limit as x approaches infinity of, well, all you have to do in this case is just multiply the top and bottom is x plus 1. So you have x squared over x plus 1 minus x plus 1 divided by x plus 1. Okay, Now we simplify this. Okay, so you write this is equal to the limit as x approaches infinity of x squared minus x squared minus x divided by, actually, sorry, x squared minus x times x plus 1 divided by x plus 1. All right, and that equals the limit as x approaches infinity of x squared minus x divided by x plus 1. All right, that's what it equals. Okay, now this is a pretty easy limit to solve, right? I think you already know how to solve this. All right, so let's solve it. Limit as x approach infinity, well, what was that? X approaches infinity of negative x divided by x plus 1. That is just, well, I mean, you see the degrees on the top and the bottom are the same, so that's just the same as negative x divided by x, which equals negative 1. And that is your limit. All right, now I want you to try valuing this limit. Limit as x approaches infinity of sine of x. What does that equal? Well, let's see how sine of x behaves, okay? So this is positive 1, this is negative 1, this is 0. All right? This is the y-axis, this is the x-axis, right? Sine of x behaves like this. Okay, something like that. It oscillates back and forth between y equals 1, y equals negative 1, okay? Does sine of x converge to any specific value as x approach infinity? No, it doesn't. All right? So we would say that the limit doesn't exist. Okay? So the thing is, trigonometric functions are cyclical, right? They don't converge to any value. They're always repeating, okay? So it's important to know that when you're finding infinite limits, or actually limits at infinity for trigonometric functions, you have to consider the possibility that they don't exist because they always oscillate. If I asked you the limit as x approaches infinity of tangent x, what do you think your answer is? The limit doesn't exist, okay? The same thing is if I ask you the limit as x approach infinity of cosine x, okay? That also doesn't exist because it's just an oscillating wave, okay? And you can say the same thing about the reciprocal trig functions, okay? So you always have to watch out for if the limit doesn't exist because the function is oscillating, okay? So now I have another problem I'd like you to solve. The limit as x approaches pi of sine of 2x divided by sine of x, okay? So when you plug in pi for x here, you're going to get sine of 2 pi divided by sine of pi, right? And that's just equal to 0 over 0, okay? So now that means you have some more work to do. So whenever you have like trig functions, you always want to consider using identities, okay? Because there's actually an identity for sine of 2x, all right? That's called the double angle identity for sine of 2x, okay? We covered that earlier in this course, where sine of 2x is equivalent to 2 sine of x times cosine of x, right? Okay? These two are equivalent. Now, this is easy because you can just cancel out sine of x from both sides, okay? And then you just get the limit as x approaches pi of 2 cosine x, which is equals negative 2, okay? So this is one example of how you can use a trig identity to solve for trig functions. Here's another problem with which involves a trig identity. So the limit as x approaches 0 of tangent squared x divided by secant x minus 1, okay? If you directly substitute 0 into this, you're going to get tangent squared of 0 divided by secant 0 minus 1, which is just 0 over 0. Okay? More work to do, all right? I wish it were that easy, but no. So now we can use our Pythagorean identities. Limit as x approaches 0 of secant squared x minus 1 divided by secant x minus 1. Okay? We can use our difference of squares rule to rewrite the numerator as the limit as x approaches 0 of secant x minus 1 multiplied by secant x plus 1 divided by secant x minus 1. Okay? You can divide them out, and then what do you get? You get the limit. You get the limit as x approaches 0 of secant x plus 1. Okay? And dash is equal to 2. So here's another instance of how you may need to use trig identities to rewrite the function so you can actually evaluate the limit. All right?